it's easy enough once you start to see things. Okay,
Yeah.
let's go ahead and get rolling. So we're going to talk about sequences, right? If my thing will scroll properly. We're going to talk about sequences today. So by definition, right, a sequence is a function whose domain is the set of positive integers, right? So in a lot of stuff, we say positive integers to mean 1, 2, 3, 4, 5, and on. You just keep counting. These are also called the natural numbers. And when you get to pre-algebra, you'll see stuff written perhaps with natural numbers for domains and things, right? So our sort of the thought process we want to work through here is that if you're given a function f of x where for 1 it's equal to 1 over x, right? Or x is greater than 0, right? We always want all of our numbers to be greater than 0. So these are strictly positive. Strictly positive inputs, right, to this function. So the outputs will be represented by the sequence called f of n, right, which will be equal to 1 over n for all n strictly greater than 0. That's what this says right here. F of n is equal to 1 over n for all n strictly greater than 0. Note that n is used to represent the independent variable in a sequence, right? A way to think about this is a sequence. Let me write this off on the side here. Do it in red. A sequence is a function that turns positive integers into real numbers, right? So we're going from Z to R. I'll explain what this means later, but this is what we're doing. This is the easiest way to think about this in the terms of stuff we've learned this semester. So a sequence is a function that turns a positive integer into a real number. So far, we've only put a real number in and get a real number out. It's helpful to think of this one as positive integer to a real number. What our chat say? Okay. For the sequence, right, sequence is represented by a listing of terms, right? So we would list them a sub 1, right? A sub 2, a sub 3, which we can also represent as f of 1, f of 2, f of 3, and so on out to f of n. And then when a formula for the nth term is known, sometimes called the general term, the entire sequence can be represented by placing braces around the formula for the nth term. So we would say just a sub n is equal to this. How you want to put the f of n back in there for this guy, all you would write is f of n equals. You don't put braces around the f of n. It's just f of n equals braces a sub n equals braces 1 over n. And this one right here, right? This is our general formula. All right. Any questions so far on what we're doing? I'll take that as a no. Okay, so our first example, we want to write down the first 6 terms of the following sequence. So I'll write these out very, very rigorously so we're not confused at all here. So our first one, remember, what are we starting with, right? What's our domain? It's 1, 2, 3, 4, 5, keep going, right? So we're going to start then, we want to do a sub 1 first. And this is going to be equal to, move this down a little bit, do a sub 1. And this is equal to, we're going to take 1 and plug it in for every n, exactly as if this said f of x is equal to x minus 1 over x. You plug in that 1 for every x. We're going to take 1 and plug it in for every n. So we get 1 minus 1 over 1, and that is equal to 0. And then we'll do a sub 2. So that is 2 minus 1 Just kidding. I can write minus 1 over 2. And this is 1/2. And we'll do a sub 3. 3 minus 1 over 3. And that is 2/3. A sub 4 is equal to 4 minus 1 over 4. This is equal to 3/4. A sub 5 is equal to 5 minus 1 over 5. That's equal to 4/5. A sub 6 is equal to 6 minus 1 over 6 is equal to 5/6. All right. Any questions on that? It's pretty simple stuff, right? Okay.
So basically,
Go ahead.
you go ahead first, Roman.
Oh, for sure. So why did you stop until the 6th term?
Because that's what it says to do. It just says write down the first 6 terms.
Oh, like on the further up?
Except where it says example 1, it says write down the first 6 terms.
Yeah, I see that. Yeah, my bad. I just read that right now.
You don't have to. Actually, so a little bit of future looking ahead. Really what you do is where these become useful is you keep writing down terms until it becomes apparent what value this is heading towards, right? So if we look at all of these terms, right, we can take these and collect them and say that these have the first 6 terms are this: 0, 1/2, 2/3, 3/4 equal 4/5, 5/6, and it just goes on. Where does this value seem to be going to? Right? If we just kept plugging in bigger and bigger numbers, right? It seems like it's heading towards 1. Right? This is sort of why we want to remember this stuff for later. And we can explain that later, but let's keep going with the next example. Okay, so for number 2, we have b sub n is equal to -1 to the n plus 1 times 2 over n. So what's b sub 1 going to be? What goes here? Just tell me what I'm going to be plugging in.
1.
Right? Plus 1 times 2 over what?
1.
1. All right. So this will be equal to, what is that? That's -1 squared times 2. And that's what? Just 2, right? Okay. Just making sure people are here and paying attention and alive. All right. How about number 2? -1 times what?
2 plus 1.
2 plus 1 times 2 over what?
2.
All right. So then this is -1 cubed times 1, which is -1. So 3 plus 1 times 2 over 3 is equal to what?
2/3.
Just 2/3, right? Because this will be -1 to the 4th, which is just 1 times 2/3, which is 2/3. And we can keep going. Do you guys already see the pattern here with what's happening with these -1s?
So it went from 2 to -1 to 2/3.
Well, just look at what's happening with this part right here, the -1.
That's getting smaller.
And well, just the -1.
Well, it keeps alternating every time, right? Because
it keeps alternating, right?
It's going to become a positive number, and then it's become a negative number.
Yeah. So we start with it's even, odd power, right? So whenever you take the even power of a negative, or whenever you raise an even number to, or sorry, a negative number to an even power, it becomes positive, right? And whenever you raise a negative number to an odd power, it stays negative. So this is alternating back and forth based off of what we plug into it. Every time we plug in, we look at this n plus 1, right? What do we know about some general rules for n plus 1? Or whenever you add things, right? Every time you add an odd to an odd, don't you get back an even number? 1 plus 1 is 2, that's even. 3 plus 1 is 4, that's even. 7 plus 1 is 8, and that's even, right? So every time we plug in an odd number, we're getting back a positive 1. And every time we plug in an even number, we're getting back a negative 1 multiplied by something. So b sub 4 is even. So what does that mean our first term is going to be? Is this going to be a positive or negative to multiply by?
That's going to be a negative.
It's going to be a negative, right? So we'll check that out. We got 4 plus 1 is equal times 2 over 4. And that is negative 1 to the 5th, which is negative 1 times 1/2. This is negative 1/2. B sub 5 is going to be equal to what? It's going to be positive or negative number,
That's going to be a positive.
right? So it's going to be positive times what? 2 over 5. So this is just 2/5. B sub 6 is a negative again. So this is just negative 2/3. All right. This one is a little confusing. Sorry about that. But do you see what's going on here? How this negative 1 raised to a power of n plus something is making this first term, or is making the output alternate back and forth, right? Our output for this is 2 negative 1 2/3 negative 1/2 2/5 negative 2/3. You see how the sign is alternating every even, right? These are all of our odds.
So we're not heading towards anything on this?
Exactly. That's exactly the case. Right. That is, if you graph this, maybe we'll graph one in a little bit. If we graph this, you'd see that it's just bouncing back and forth, and that's called oscillating. Okay, so this one, C, we have a piecewise definition for this sequence. So let's take a look here. It says that C sub n is equal to n if n is even, and 1 over n if n is odd. So what's our first number we're going to start with? C sub what?
Two.
Well, why are we going to start with 2?
1 over 1?
Well, you know, I'm not worried about the output. Just we're going to start with just 1, right? So is 1 even or odd?
Odd.
That's odd.
Right. So we have to use this lower part. So this is equal to 1 over 1, which is just
Right.
1. How about C sub 2, right? Is this even or odd?
That's even.
It's even. So then this is just what?
2?
2. C sub 3, back to odd, 1 over 3. C sub 4,
That's just going
4.
to be 4.
C sub 5 is 1 over 5. C sub 6 is just 6. All right. So our output for this guy is 1, 2, 1/3, 4, 1/5, 6th, and it just keeps going. All right, cool. We could graph a couple of these in a little bit. That way you guys can see what's going on.
So those ones are oscillating, but in a positive domain?
So what you'll see here, right, it's kind of hard to tell. That is correct, but not quite. This guy, if we were to graph it real quick, just show you a quick sketch of it. It is correct that it's all positive, right? But we have 1, 2, 3, 4, 5, 6, right? So at 1, we're at, we'll say this is, let's do this up here. We have plenty of room. We only go up to 6. So let's do 1, 2, I'll just do up to 3. Well, I got to do at least to 4 so you can see what's going on. 4. All right. So at 1, we're at 1, right? And then at 2, we're at 2. And then at 3, we're at 1/3. So I don't know, we'll put it right here. And then at 4, we're up here at 4. At 5, we're at 1/5, which is even smaller. And then at 6, we're way up here at 6, right? So you can't really put a line between these because that's not how it works. Because we're plugging into real numbers. You can't really, we don't have a value here at 1/2, right? Because even though we're plugging into real numbers, so you would think, okay, well, there are real numbers between 1 and 2. You have to remember our domain is just positive integers, and there's nothing between 1 and 2 in the positive integers. It just goes straight from 1 right to 2. There's no 1/2, no 0.67, none of that stuff. So there's nothing we can plug in here. So we can't really graph, like we can't do like this. That's not acceptable. You can't do that. But what we can do is these values, every odd value seems like it's going closer and closer to what, 0, while every even value is just taking off and going straight up, right? So it is oscillating in a strictly positive way. But that's not quite how you describe it. But for right now, we'll say that that's the case. Okay. Any questions on any of that? Like why you can't graph anything between 1 and 2 or anything like that?
Why can't you graph anything between 1 and 2?
Gotcha. Okay. So let's roll back up here. So we want to remember that a sequence is a function that turns positive integers into real numbers, right? So remember, it's a function whose domain is the set of positive integers, right? So in the positive integers, right, the integers, if we want to look just at integers, right, we'll say just integers, which is represented by this really poorly drawn blackboard R. This is equal to the set say -3, -2, -1, 0, 1, 2, 3, and so on, right? Integers are whole numbers, right? So there's no partial remainders, there's no fractions, there's no decimal expansions, there's no irrational numbers. It's just real whole numbers, right? So in the integer, you can't say something like this. This symbol means element of. If you put a line through it, it means it's not an element of. So there's no such thing as 1/2 as an element of the integers. That doesn't make any sense. There's no 0.012 is not an element of the integers, right? There's no 4/5. That's not an element of the integers, right? The number e is not an element of the integers. Pi is not an element of the integers, right? Only whole numbers are integers, right? So you could say that like 0.12 or 0.1/2, right? Or sorry, 1/2. This is what's called a rational number. Remember we talked about rational functions this semester? So this is a rational number. So we represent rational numbers with this thing that's, you put a Q, it's a blackboard Q, stands for quotient. But this is a rational number. 0.12 could be a rational number. when it's represented as a fraction, but as a decimal, it's a real number. E is an irrational transcendent number. It's what's called a non-algebraic number because there's no way for us to define it by just adding other numbers together or multiplying, dividing, subtracting other numbers to get to E. You actually, in order to define E, you have to use a series, and a series is based on sequences. That's why we're learning these things. Same thing with pi. You can't add numbers together to get to pi. You have to find some other way to define it. So pi is another one of those ones that we call a non-algebraic or transcendental number, and that one is a real number. So why we can't add anything between 1 and 2 into here is because the domain for our function, right, all of these right here have to come from the set 1, 2, 3, 4, 5, and so on, which is the set of positive integers. These numbers right here, take this whole thing, scoot it to the side. Whoop. These numbers right here are y's. These guys are real numbers. These outputs can be real numbers, but these ones right here, there's we can only put in positive integers. And since there's nothing between 1 and 2, nothing between 2 and 3, nothing between 3 and 4 in the integers, nothing to put in. Does that make sense?
Yeah.
Okay.
Thank you.
Yeah, not a problem. Sorry, I like to beat things to death. It's my bad. All right. So the next thing we're going to work on, the next example, is we're going to determine a sequence from a pattern, right? Now, something that may throw you off a little bit, I literally just said that E isn't in here, but notice we're not plugging E into anything, right? What's changing? Because what's this first term? Let's take a look at this first term here. If we wanted to make this first term look like the rest of these terms, we could do this, right? We could say e to the first over 1, and then we have e to the second over 2. We have e to the third over 3, and so on, right? So what does it seem like we're doing here every time? We're just raising the number e
and then dividing it by the same,
and then
whatever the
dividing
power
it by
is.
the same number we're raising it to. So we could define this as a sub n is equal to, braces, a sub n is equal to e to the n over n. Does that make sense? I'm gonna assume that's a yes. Okay.
Yeah.
So we have our next one here, right? We have 1, 1/3, 1/9, and 1/27. And again, I'm going to rewrite this first one as 1 over 1 to also make it a fraction like the rest of them. All right. Now, something I want you to think about here. This first term, right? This first term is, this is b sub 1. This is b sub 2. This is b sub 3. And this is b sub 4, right? So that means that whatever we did for this first term, we plugged a 1 in. Whatever we did for this second term, we plugged a 2 in. Whatever we did for this third term, we plugged a 3 in, and so on, right? Does that make sense? So when we define this, what does it look like we've done for the first term here? It's more helpful when I try to figure out the pattern for these. I try to think about it as just thinking from the terms that are very obvious. Like to me, this 1/3, 1/9, and 1/27 are very obvious how to get those. The hard part's figuring out how we go back to this first one, 1 over 1. But let's just think about it for a second. Let's think about these b sub 2 to b sub 4 first. what is 1 over 3? As what do you notice about 1 over 3 to just 1 over 9?
3
The
negative.
denominator is squared.
Of second power.
Yeah.
Yeah, it's squared, right? And how about 3 to 27?
It's cubed.
It's cubed, right? So
But is it a negative value?
Well, it's not a negative value, right? You could do this as a negative value. Let's not do it as a negative value, and I'll show you why. Because it'll be easier to not do it as a negative value. But let's think about this, right? If we plug in a 2 and we get a 3, right? If we're saying that it's the denominator raised to some power, we're plugging in a 2 and get a 3 and get a 9, a 4 and get a 27. What power do you have to raise 3 to in order to get 3?
1.
1. What power do you have to raise 3 to in order to get 9?
2.
And what power do you have to raise 3 to get 27?
3.
3.
Okay. So if I have to raise this one to the first power, but I'm plugging in a 2, what do I have to get to 2 to make it 1?
1/2.
1. 4.
Simpler than that. Because
Subtract one.
look at the next one. What do I have to?
Somebody just said it.
What was it? -1, right? So instead of doing a negative power, why don't we just say this? It's 1 over 3 to the n-1 power. You guys see why that works? Because if I plug in a 1, right, then 1 minus 1 is 0. Anything to the 0 power is 1. That gives us 1 over 1, which is our first term. 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. All right, does that make sense? So sometimes it's easier to try to think about these as what are the terms later on doing and seeing how we can go back to the earlier terms.
Show them why you can't write it as 3 to the negative n, because I know that was suggested.
Yeah. So the reason why you can't do that, right? Let's just say it's 3 to the you'd still have to do n-1, right? But this is why you can't do that. If we said it was like this, then our first term is what? Our first term is 3 to the -0, which is 1. Our next term is 3 to the 2 minus 1 is 1 to the -1.
No, I think that works out. It works out, but
Yeah.
I think somebody had said that why can't it be 3 to the negative n, not negative
Oh.
n-1?
Oh, gotcha.
Yeah,
Just
because that will still work out.
Yeah. So if we do just to the negative n, right, like this, then that's going to be equal to 3 to the -1 is 1/3, and then 3 to the -2 is 1/9, and then 3 to the -3 is 1/27th, and then 3 to the -4th would be 1/81, 1 over 81. And this is not the same sequence. So
You're missing that leading term of the sequence.
yes, the 1 isn't in there. So we got to have that -1.
It's a good thought, though, because you could think of 3 to the negative n and figure out, okay, how can I build off of this to get that leading term of 1 that's in the sequence? So,
Exactly. So if you got to this point, right, and you can take a look here and you go, okay, I have everything but, because if we look at this one, if you'd plugged in one more number, you would have gotten 1 over 81. So you can take a look at this one and say, okay, what can I do to this to get this first number? And you can work back to say, okay, well, let me try, how about subtract 1 from n?
perfect.
And that'll get you right over to there. All right. So on this one, again, we're going to write this out very explicitly, and I'll say 1, 3, 5, 7. And this is C sub 1, C sub 2, C sub 3, C sub 4, and I'll even write this as equal to f at 1, f of 2, f of 3, f of 4. Okay, so what does it seem like we're doing here?
Can I take a wild guess at it? And it's 2 times n minus 1.
Heyo.
Hey, there you go.
Damn,
Well,
dude.
actually, hold on. Let's take a look. Let's take a look, though. I think that's a good guess, but let's take a look. Let's assume that this is 2 times n minus 1, like this, right?
Yes.
Okay, this will probably work. So this will give us what? The first number is 2 times 1, which is 2 minus 1 is 1. And then it's 2 times 2, which is 4 minus 1 is just 3. 2 times 3 is 6 minus 1, 5. Yep, that works out, doesn't it? There you go. All
Very
right.
nice. Nice job.
Good job. For a second, I thought you meant this. So I just wanted to make sure. This is not, these things are not the same thing, right? So that's it in one go. Good stuff. Okay. Let's take a look at this one then. $25. Again, this is C1, F at 1, C2, F at 2, C3, F at 3, F at 4, and finally C5, which is equal to F at 5. This one's a little bit harder.
It's
At
just
least
n
for me.
squared.
Just squared. Yeah.
It's just squared, right? There you go.
There you go.
So there you go. This is equal to a sub n. Boop, boop, boop. I put c's. Oh well. We'll call it just n squared. There you go. Well, it was a little bit harder for me the first time I looked at it this morning. Okay. All right. So same deal, right? What does it look like we have going on here? If we remember when we talked about earlier, right? This, look at the signs,
Oh, they're oscillating.
right? So based off of the earlier example, this in part has to have something that looks like what?
1 minus n.
Now 1 minus n, right? To get this alternating sign, I tried to beat this dead horse earlier.
Or n
To-
plus 1.
Don't
Right.
you need the?
The negative.
Well, we don't know exactly what it'll be. The first thing you want to always think is, this is sort of what you want to think. Erase this real quick. Alternating signs mean -1 to something, right? Is some manipulation of n. It could be n to the n, it could be n plus 1, it could be n divided by a number, it could be all kinds of stuff. But we definitely know, no matter what, if we have alternating signs, we have to raise -1 to some n power, or some power of n, right? So I'll put that instead of some manipulation, some power of n. Some power of n. So let's figure out what -1 is doing first. So when we plug in 1, we get back a positive, which means this -1 had to be raised to an even or odd power.
Then
An even power, right? And then when we plug in 2, it comes back negative, which means it had to be raised to an odd power. So it seems like n plus 1 from above is going to do the job.
And is it over n? Okay.
Let's see. Yeah, that's it, right? Well, yep. You can just do it just like that. It's just over n. So we'll write it like this. We write this a little bit better. It's just -1 to the n plus 1 over n. There you go. That should do it. This is going to be equal to 1 over 1, which is 1, and this is -1 over 2. This is 1 over 3, -1 over 4. Yep, it works out perfectly. There you go.
Yay!
That easy.
All right, I'm going to cheat code this.
Yep.
Right? So for the fifth one, do the odd and even sequence.
Oh, gotcha. Yeah. Okay. So just the odd sequence, right? So you could also say that this is equal to, what is it? It's
it's n. Oh, 1 over n.
1 over n if n is odd.
Uh-huh. And then
it's -1 over n if n is even. That's
yeah.
even easier. Even easier.
It works. There you go.
Oh, right. And that's it. That's sequences.
Cool. That's sequences, y'all. Fun, huh? Like, yeah,
Yeah,
sure.
they're pretty fun. They're like solving puzzles and stuff.
Yeah.
So yeah, sorry.
I'd rather do logs.
It's just a different style of math, but you'll see sequences in Cal 2 for sure.
Yeah. So just to come back up here real quick, right? The very first one we started with, right? The very first example it gave us f of n is equal to 1 over n. Sort of where this goes forward, right? Just a preview of what goes forward. Goes forward. If I gave you the sum from n equals 1 and run it to infinity of 1 over n, what does this equal? Right? This is where this stuff comes important. This is called an infinite series. Infinite series are important because this is how your calculator works, right? Your calculator cannot analytically solve things like a log, or it can't analytically solve a problem like a calculus problem. It can't do that. It's not intelligent. So we have figured out how to define things like a polynomial based on an infinite series, or the value of pi based on an infinite series, or the output of a sine, right? You want to figure out what sine of some angle is, infinite series. So that's one application of these things. This will come back in Cal 2. Series and sequences are really important in this stuff called number theory. And abstract algebra, also really, really important in computer science, like incredibly important in computer science. This kind of stuff is the foundation of the math that's necessary for like public key encryption, which if we didn't have that, we couldn't do online banking. It wouldn't be secure. So super, super applicable to the real world, even though it's kind of abstract.
Woohoo! All right.
And
Any questions on sequences?